Hi all, welcome to the Immersion Group presentation, part of the Advanced Cooling Solutions group. This presentation is about the upcoming white paper with the design guidelines for immersion-cooled IT equipment. This presentation is going to be held by myself, Rolf, Brink, CEO of Asperitas, by Rick from Flex, Leonard from 2 Series I, and Jimil from 3M. I'm also covering in this case for Jessica, who was supposed to be part of this presentation but couldn't make it in time, and she's from Intel. The focus area of this white paper is to highlight key areas for IT gear, which is designed for immersion. This presentation will cover the thermal design considerations, mechanical guidelines, some software adjustments that are relevant to consider, electrical validation and material compatibility, and all these aspects are relevant for optimized IT equipment for immersion. Keeping these areas in mind when designing IT gear will allow you to increase the potential performance and all the promises of immersion technology towards the future. So thermal design is probably one of the most interesting parts of optimizing IT equipment for immersion technology. When looking at the thermal design of a solution, a basic division can be made between single-phase applications and two-phase applications. So single-phase refers to a solution where the liquid is not designed to evaporate, and which is driven by either forced or a natural convection circulation mechanism. The enhancements that can be achieved in various ways. First of all, the liquid circulation is relevant, as mentioned before. Both forced and natural convection can be used for single-phase immersion cooling. Forced is when a pump is used to circulate the flow, while natural convection relies on density variations with temperatures when hot liquid rises to the top of a tank. Air design heat sinks are very often used in single-phase immersion applications. However, due to the inherent flow resistance of air design heat sinks, these designs will still rely on natural convection through the heat sink, even when forced circulation is applied, unless mechanical flow is directly ducted to the heat sink. To improve the effectiveness of a heat sink, it should be designed for immersion by maximizing the flow through the heat sink. Enhanced performance will be achieved by getting colder liquid to the hot components as well. Further heatsink enhancements can be achieved by increasing flow rate from a laminar flow to turbulent. So a laminar flow builds up thick thermal boundary layers, which reduces the thermal performance. These boundary layers can be reduced by increasing the flow rate and achieving a turbulent flow. However, with the relatively high viscosity of immersion liquids compared to air, a turbulent flow may not be achievable, and the next best thing is then to create an unsteady flow that can break up the boundary layers and enhance the thermal performance compared to laminar flow. For two-phase immersion, the approach is different compared to single-phase immersion. In two-phase immersion, the immersion liquid has a relatively low boiling point. So when the liquid reaches the hot components, the liquid is experiencing a phase change to gas, and there's a boiling going on. The gas rises to the top where the condensator is located, and the condensator cools down the gas, and it's returned to liquid and can be reused for the cooling process. To make this process as efficient as possible, the heat sinks on the high-powered components should be replaced with simplified heat sinks that are flat plates with boiling enhancement coating. The boiling enhancement coating introduces and enhances the number of nucleation sites and where the phase change is first initiated and bubbles are being formed. It's not only the formation of bubbles that are of importance for enhanced heat transfer, but also the re-wetting of this boiling enhancement coating. The re-wetting makes sure that the liquid is there to replace the one that just changed phase into gas or a bubble. One of the advantages of immersion cooling is that the immersion liquids have better heat transfer properties than air and is therefore more efficient in removing the heat from the hot components. This allows for not needing heat sinks on low-powered components on the board. And to show how these liquids, going a bit too fast, to show how these liquids are all similar across the board, I've chosen to show here a table representing the specific heat comparison of the different liquids. So the two most predominant liquids are hydrocarbons and fluorocarbons, and there's a significant difference in specific heat. However, the volume of liquid per kilogram is also very different, whereas the hydrocarbon has a much lower density than fluorocarbon does, which means that if you compare the amount of joules that can be transported per liter, these liquids perform almost identical when it comes in their heat capacity capability. And not only specific heat here is relevant, because flow rate is as well, and that combination is what gives you a good indication of what liquids can do. So one of the ways of optimizing for single-phase applications is to optimize the heat sink design parameters. These parameters can be divided in a couple of topics. Most relevant, most important is probably the fin pitch and the fin specification. This determines, first of all, with the fin pitch, how easily liquid can flow in between the fins of a heatsink. Second relevance is the fin specification, so the width and the height and the thickness. So how that determines the ability of thermal energy to actually reach the extremities of the fins. You will find with proper analysis that a lot of the thicker fins will allow the energy to spread closer towards the fins extremities, which allows more effective use of surface area of a heatsink in liquid, whereas an air design heatsink doesn't really utilize the fins that are applied onto a heatsink. Now, another consideration is the heatsink base, which is responsible for spreading the heat, whether it's a vapor chamber or a solid material. The heatsink base must be able to distribute the heat effectively towards the fins. This is also a consideration in air, but much more so with liquid because of the superior characteristics of liquid in absorbing and transporting the heat from one material into the next. Now, the liquid and flow characteristics are related to the fin positioning, fin design, and the angles in which the fins are placed, and these can differ per application. Another important consideration is the component placement in the tank. Thermal shadowing is something to take into account with single-phase applications. A component that is placed deeper into the tank that has let's say a CPU that has a second CPU in its direct path in an upwards direction will create a thermal shadow, which means that the upper heatsink will be getting the preheated liquid from the bottom heatsink. There's also a temperature gradient running through a vertical oriented chassis inside an open bath single-phase immersion technology. The lowest point in the bath will usually have the lowest temperature, whereas the highest point in the liquid will carry the highest temperature. Simply put, warm liquid wants to move upwards. That means that highest powered components or components with very stringent temperature requirements should be placed deeper into the liquid and therefore more towards the rear of the chassis. Whereas high temperature tolerance components or components with only minimal thermal properties are usually safe to place in the upper side of a chassis, more towards the front. When looking at a thermal design for two-phase liquids, the immersion heatsink design parameters are most relevant. So first of all, as just explained, the boiling enhancement coating. Here on the image, you will see a couple of examples of what this enhancement coating looks like. The coating thickness and particle size is of relevance, and the coating base on the integrated heat spreader or boiling enhancement coating is a relevant consideration. In this presentation, Jimil Shah from 3M is also present, and he can elaborate a little bit further. Jimil, would you like to add to this slide as well?
So direct submersion of a bare die or leaded package is not an optimal way to do two-phase immersion. So for passive pool boiling heat transfer, you need the boiling enhancement coating on the IHS or integrated heat spreader, or a heat spreader which will work as a heat sink on the top of the leaded package. So there can be multiple ways, can be various techniques can be used to enhance boiling heat transfer, and that is called as boiling enhancement coating, which increases the surface area on the top of the boiler. So there are various techniques, right? So it can be extended surfaces like metallic or graphite fins, or foams, or porous organic coatings. And the most common way of doing this is porous metallic coating, where you can use the copper particles fused with silver, and you can either use different techniques like plating or sintering or brazing on the top of the heat spreader and make the boiler. And you can provide a retention mechanism as shown in the figure along on the top of the processor, and you can make the heat transfer coefficient effective. So the coating, the surface area varies from the coating thickness and particle size. Ideally, it is in the range of around 100 to 100 micron, but it can be improved or increased based on the requirement of the total heat flux. The major advantages of two-phase immersion cooling would be the constant and isothermal temperature environment. So it provides much even thermal profile in the tank as compared to other cooling techniques. And there is no thermal shadowing because all the components in the tank will be at the same temperature, which is the boiling temperature of the fluid.
So there's also no thermal shadowing, right?
So there is no thermal shadowing. Yeah, it's the constant, it's the isothermal temperature environment.
All right, thank you very much, Jimil. Let's continue to the next couple of slides.
Welcome everyone, and thank you for attending. My name is Leonard Ciubotaru. I'm a research engineer at TUSRSI, and I'm in charge of Special Project Division within the R&D department. I will continue this presentation with the mechanical design guidelines for immersion. When designing a server for immersion, we can follow the classical mechanical design principle. Nevertheless, there are some specific key factors to keep in mind that I will detail in the next couple of minutes. Chassis dimensions. There are several different forms, sizes, and technologies for immersion tanks. One just needs to adjust to the size of the tank for which the server is designed. The important factors to bear in mind are allowing for easy fluid circulation and ergonomics, since the chassis are vertically extracted and not horizontally like a classic racked solution. In order to meet data center handling requirements, the total mass of a server with all the components installed must not exceed 34 kilograms or 75 pounds. If the server is more than 18 kilograms or 40 pounds, it is recommended to be handled by 2 people. For permitting easy handling, the chassis needs to be equipped with handles for manual manipulation or otherwise with some sort of attachment fixture for mechanical manipulation. As a difference from the rack servers, we recommend paying special attention at the mechanical resistance of the front side of the chassis, where the vertical pulling forces will be applied, and reinforce this part accordingly. Components positioning. The component should be positioned in such a way as not to hinder or block the thermal flow, or otherwise said, the movement of the immersion liquid. The positioning should allow the most surface contact in the direction of the liquid movement. For example, the heatsink fins should be parallel with the thermal liquid flow. Special attention should be given to plug-in components like PCI connectors. since the servers are installed in a vertical position. Could be that some type of fixture needs to be implemented to keep the components from disconnecting. Power transmission. The servers can be powered via cables or busbar. Both solutions work in immersion. If cables are used, one should make sure the cables have enough length and space to pull out the chassis. Preferably, upper side connection for cables should be used. If the power is transferred via busbar, then one must ensure the floatability of the blind mate connector and guiding features to facilitate the alignment. PCU or power shelf. According to the tank configuration, both PCU and power shelf can be used. Each of these options has its benefits and drawbacks. PCU modules can be fully submerged, either near the bottom of the tank for optimized cooling or at the liquid level for ease of access. We recommend removing, disconnecting, or shutting down via software the PCU fan. From the accessibility point of view, the power shelf presents obvious advantages. The power modules are accessible from the top of the tank, which facilitates servicing or replacement. If a power shelf is used, most probably the tank will have busbar installed. We recommend that this busbar be positioned out of reach of the operator and that they should be protected from possible falling debris. Also, the server should be designed in such a way that some sort of hard stop can provide a security from damaging the power connector if the server is dropped or badly placed. This was a very brief description of the mechanical design guidelines for immersion. Please don't hesitate to ask your questions following the presentation or contact me afterwards.
So far, 2 Series I, thank you for that. The software portion of IT design is also of relevance. First of all, the thermal optimization parts require focus on temperature settings and optimized thermal protections. And this is due to the increased heat capacity, which allows for much higher thermal tolerances. Imagine an air environment that is being cooled with 35 degrees Celsius cooling and CPUs running at 80 or 90 degrees Celsius at the maximum performance. Within liquids, the same environment might allow you to work with much higher temperatures. That is the same IT equipment. So an environmental temperature of 50 degrees may be very suitable for that same IT specification. Another factor to consider is the increased heat capacity, which allows for much higher thermal tolerances of the components themselves. CPU turbo boost capability can be drastically increased, or can be even further increased than what normally is possible, which opens the door to a much more common type of overclocking. Next thing to consider is the system management capabilities, or the BMC. Fan control and detection is something that is widely known to be a factor for immersion. So fan support in immersion should be disabled. So the fan detection, fan safety mechanisms should all be disabled when you're dealing with a server that is immersed in liquid. Usually, most vendors or most integrators will remove fans to allow liquid flow, to promote liquid flow further, and that detection should be disabled. Reporting possibilities are of a next feature which can be added to BMCs or system management protocols, which is focused on monitoring liquid temperatures as opposed to air temperatures, to monitor flow rates or liquid quality. These are the type of sensory data of telemetry which servers could potentially start reporting on when optimizing system management protocols. And finally, there's the firmware. So when looking at BIOS possibilities, one of the things that could be considered is, especially when designing IT equipment, in essence, both for air deployments and liquid deployments, is to allow an end user or an integrator or an immersion technology vendor access to certain options to disable thermal protections, depending on the type of immersion technology. There's, for example, an option to select predefined set of immersion optimized settings, like what kind of intake temperature would be engaging, what kind of safety protocols. Another possibility would be to implement an immersion optimization switch, a physical switch, which affects safety or temperatures or boost settings, things like this. Customized firmware is something that is already happening now and then when it comes to larger deployments, which manufacturers often support. And that is often firmware that is released to vendors and integrators, but this should actually be a standard consideration when developing RT equipment or optimizing it for immersion. Custom SKUs are at the next level. When we're looking at the way that CPUs or chips are designed, they are designed predominantly for air environments. When designing these fundamentally for liquid, as in liquid only, the shape and size of components can be changed quite drastically. And that is something that we would like to open the door for within the OCP immersion group. On the electrical topic, I will hand over to Rick Payne from Flex, who will tell you a bit more about the electrical optimization for immersion.
Hey, Rolf, thank you very much. Yeah, I'm going to cover a few slides on the electrical, a few key points. Obviously, with immersion, it will enable the use of the CPU to really extend its ability to cook. You know, in other words, turbo process for higher performance that you might not be able to get in your conventional forced air cooling. Reliability is a key factor as chips like CPUs, from a thermal perspective, migrate at a higher limit and back down to a lower limit. That tends to degrade the reliability of components. So being able to manage a component like a CPU at a nominal temperature throughout its life cycle will extend its reliability. And then component placement can be optimized to improve latency. And so the point there is that in a lot of designs today, component placement is somewhat dictated by thermal management. So if that requirement goes away, for lack of better terms, because you're immersing the components into liquid cooling, then you're able to optimize the performance by coupling components closer together, and in some cases reduce your latency that you might see. Fans aren't required. I think everybody knows that. And sensor placement throughout the system is really important to understand what's going on with the liquid cooling from top to bottom. So what's important to note here is that any electronics that's designed for immersion doesn't really get a mulligan to bypass any of the due diligence that you do from a quality perspective for electrical design. So what's really important to do is make sure that you've got a really robust test plan that really looks at the key components of any electrical design, which signal integrity, loss measurements, power consumption and loss, and etc. What I would recommend is that as your test plan is fully baked out, that you look at some of the key data points from your test plan in and out of immersion to make sure that you understand the deltas that you're starting to see from using immersion technology. The community is growing. Immersion's being used more widely now than it ever has. There's a lot of data on this out in the world that you can go out and search for. So I highly recommend that you focus on a very detailed test plan. You look at the impacts of immersion that may have on your technology and your platform that you're going to immerse, and that gets implemented into your test plan. So thank you. With that, I'd like to pass it over to Jimil. Jimil, take it away.
So thank you, Rick. So as Rick rightly mentioned, this material compatibility with regards to immersion cooling is very important, because not only thermal performance, but the physics compelling the reliability and the material compatibility is also very important. because whenever you go to the IT equipment market, everybody will ask you the first question, like what are the material compatibility challenges with respect to immersion cooling, because there are so many types of fluids available, hydrocarbons, fluorochemicals, and there is no such standard exists in the global market. It's not about the problem statement, it's all about the failure. And because it's a very important chapter with respect to IT gear immersion cooling, so this chapter suggests experiments for predicting degradation of cables, printer circuit boards, packages, optical fibers, passive components, and etc. We have covered a wide range of common examples and better materials, and also the testing methodologies for different cooling methods, whether it is single phase, two phase, using hydrocarbon fluids or fluorochemical fluids. So in the better material list, we have covered servers, cables, connectors, power supplies, storage, high-speed networks, and all types of components. Because here we are dunking the whole server inside the dielectric fluid, so the fluid is going to be in contact with each and every component. And how will it affect on the chemical composition base? How will it affect on the thermal performance base? Everything should be covered. We are also talking about the components to check for compatibility and material source of contaminants. For example, in air-cooled environment, the effect on the reliability of components would be from the gaseous and particulate contaminants when you use airside economization or free air cooling. So similarly, in immersion-cooled environment, the electronics and also the supporting equipment like cables that you're putting themselves inside, and they may act as a source of contaminants. So we are also trying to cover, we have provided the table which outlines common examples for, I would say, to take into consideration for such validation. With respect to material compatibility and the test methods, so basically material compatibility for single phase immersion cooling with hydrocarbons, we have provided different test methods. We have some ASTM standard test methods like D471 or D2210, which are existing in the market for transformer oils. But with the right modifications, we can utilize them for the immersion cooling purpose for hydrocarbon oils. First test is general material compatibility, which you are actually certifying the server which is under the operation. So first you do visual inspection, you check for the effects of contaminants, pool of oil, and also you check for thermal testing, thermal performance, and also you do microscopic images by doing cross sections and that kind of test. Second is doing the age testing, because it's the ASTM CHEDEX standard is not applicable for immersion cooled environment. It is only applicable for air cooled environment because of the heat capacitance difference between the oil and the air. So the accelerated thermal cycling will not be applicable here, but thermal aging can be a good source of experiment. So the second test has been mentioned about material compatibility by using like hydrocarbon oils again for age testing of shoulders, QSPFs, and different components, active components, passive components, PVC cables, optical fibers, all of them. Now the material compatibility for fluorochemical fluids is a little bit different. When we talk about fluorochemical fluids for single phase application, so most of the equipment in the electronics are hydrocarbon polymer materials, right? So basically the fluorochemicals are so inert, they don't have a direct affinity or direct reactivity with any of the materials, but they may, but you might observe, because one hydrocarbon polymer can observe swelling of another because of the hydrocarbons from the fluid. So this is called secondary incompatibility, where fluorocarbons merely act as a contaminant vector, because once they have some hydrocarbon polymer absorbed in that fluid, now that will be absorbed by the another hydrocarbon fluid, carbon material. So, but in the case of single phase immersion cooling with respect to fluorochemicals, these kind of incidents are very rare. But when we talk about two-phase immersion cooling, so for two-phase immersion cooling, only fluorochemical fluids are available as of now, and the material compatibility is a little bit different because now you are talking about boiling. So the relatively non-volatile hydrocarbon contaminants dissolved in the fluids are deposited on boiling surfaces by distillation in much the same way that lime accumulates in a tea kettle with time. So the vapor evolved by boiling the fluid, being freshly distilled, now it's free of hydrocarbon contaminants. And once it's condensed, it can have another, I would say, a high affinity for hydrocarbon contaminants, and the cycle continues. So to take care of those kind of challenges, we have mentioned about substrate extraction test method for two-phase immersion cooling using the fluorochemicals is the very straightforward test method, 48-hour test method, and which can be found in different publications. And we have also provided the guidelines for adsorption and swelling in the IT gear guidelines white paper. So I would like to open the forum for the community and feel free to ask the questions. I would also like to urge the people, the vendors, and also the end users to come and engage in the community activities related to immersion cooling, because it gives the boost to the ecosystem, as well as it also helps in determining the standards. So it is an opportunity for us that OCP has given us to come up with the first ever standards related to immersion cooling, and it will be a great interactive section between the end users based on the requirements and vendors based on their solutions they are providing. So the documents and mailing lists are available, and for question and answers, feel free to ask any questions or reach out to us after the session. Thank you.